Namaskar. Welcome to the SERB seminar. And on behalf of Professor Sandeep Verma, Secretary SERB, I welcome all of you to this wonderful seminar today. आप सभी का स्वागत है. The COVID pandemic offers a unique opportunity for radically reforming India's healthcare system, which needs to be prioritized and escalated through infrastructure, investment, and manpower. Despite being on the list of essential medicines prescribed by the World Health Organization, oxygen remains a precious commodity, especially under conditions of medical distress, such as we saw earlier, and even the present situation of unabated COVID infections, bringing great mortality burden to the afflicted patients. Low oxygen availability, continuous and reliable supply of pure oxygen, and innovative accessories to deal with unusual oxygen demand were critical during the peak of COVID-19 infections. One may continuously need of indigenous oxygen concentrators with India-centric innovations in providing supplementary oxygen to hospitals, wards, and ICUs, and to patients under home isolation. तो भारत ने जिन संकटों का सामना किया है, बहरहाल सेकेंड वेव की बात अगर हम करें तो आज हम बात करेंगे आपके साथ ऑक्सीजन की और किस तरह एक यूनिक टेक्निक बनाया गया है उसके बारे में बात करने के लिए आज का टॉपिक है इंट्रोडक्शन टू PSA टेक्नोलॉजी एंड इट्स रोल इन लॉन्ग टर्म ऑक्सीजन सॉल्यूशन फॉर हॉस्पिटल्स. वी आर वेरी प्रिविलेज्ड टू हैव विद अस प्रोफेसर Sandeep Verma, Secretary, Science and Engineering Research Board, to welcome our very esteemed guest, who is none other than Dr. Ravinder Bansal. But before I request Professor Sandeep Verma to say a few words, I would like to tell you a little more about Professor Verma. His work has been recognized by Distinguished Alumni Award of Banaras Hindu University, the Shanti Swaroop Bhatnagar Prize, the DAE SRC Outstanding Investigator Award, and the Swarna Jayanti Fellowship, to name a few. He is an elected fellow of 3 national academies, Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences. It is now my privilege to request Professor Sandeep Verma ji to say a few words on today's seminar. Sir.
Namaskar. Thank you very much, Nidhi Kumar ji. I'd like to welcome Dr. Ravinder Bansal on this very nice platform that we have today, where we are going to listen to his expertise in oxygen generation, concentrators, as well as, whole lot of innovations that revolve around this particular commodity, as Nidhi ji pointed out, which has been under the spotlight given the pandemic situation. India struggled a lot. And now what we have done is, as part of our research ecosystem, research R&D thrust, SERB, which is Science and Engineering Research Board, part of Department of Science and Technology, Government of India, we are trying to come up with strategies whereby we can innovate in an India-centric fashion of these concentrators, of these oxygen generators using PSA technology. And when you are going into the areas of new inventions, who better to seek assistance, guidance, and valuable inputs than somebody who has been at the forefront of oxygen generation innovation, which is our speaker for today, Dr. Bansal. His name was, suggested by our secretary, Professor Ashutosh Sharma, who did mention that we are going to listen to somebody who's absolute authority in this area, not only from research point of view, but also from the standpoint of actually making this work, the entire translation, and close to 80% of the oxygen installations belong to the company he started in the United States. So we are very proud and privileged to know Dr. Bansal, his outstanding success. And as scientists and as technologists, as engineers, as people who would like to become self-reliant in the oxygen generation capacity, we look forward, sir, to your webinar today. And I'm pretty sure that a lot of people who have joined directly and many more who are going to listen through the OTT platform would benefit, including the startups. So we would like your ideas to be percolated all the way down to startups and the companies who are proficient in making such devices. Without taking too much time, I would like to thank Dr. Bansal, thank Nidhi Kumarji and Vigyan Prasad, who have taken up the challenge of making this webinar work and available to many others. I close my brief remarks here. Thank you very much, and I'm looking forward to great talk on PSA and related innovations. Thank you, sir. Thank you, Nidhi.
Thank you, Professor Verma. I would now like to welcome Dr. Ravinder Bansal. Dr. Ravinder Bansal is the former Chairman, Chief Executive Officer, and co-founder of AirSep Corporation based in Buffalo, New York, USA, with sales in over 100 countries. AirSep is the largest supplier of PSA oxygen plants for hospitals in India. Dr. Bansal earned his PhD in mechanical engineering from the Georgia Institute of Technology in 1977 and worked at Linde prior to co-founding AirSep in 1987. And under his leadership, AirSep grew to become the world's largest manufacturer of PSA oxygen systems. He sold AirSep in 2013, and after that, he will be sharing today's very important topic today and his long-standing expertise on PSA technology for long-term oxygen solutions. We welcome you, sir. Please come and share your thoughts on this topic today, sir. Dr. Bansal, sir. Are you on mute, sir?
I suppose his connection is frozen.
I know. So there'll be a lot of possibility of a lot of questions, Professor Verma, today. What is the difference between oxygen concentrator, oxygen generators under this PSA technology? How do we utilize this? How do we actually transport it? Because दिक्कत वहीं आई थी transport करने में oxygen को. And people need to understand that there is an industrial oxygen and there is medical oxygen. I think we've lost him. So I welcome the audience once again. And we'd love you to flash a few questions and share your vision on long-term oxygen solution for hospitals till we get the link back. Because India's health sector can emerge as its biggest driver of growth in employment in pharma, biopharma hospitals, where it is required by nurses, medical equipment, and it's got a huge multiplier effect. So if you can tell us a little bit about SERB for the viewers, sir.
Absolutely. So thank you, Nidhi. If we stick particularly to this oxygen related problems, what we have done, and perhaps you and other viewers would recall, SERB is one of the largest funding agency at the moment in India, with close to 150,000 investigator base that is associated with us. And we are going to have a dedicated research call, which is going to focus on oxygen generation. And I'm happy to share, we have now Dr. Bansal back. He's one of the experts who is going to guide SERB in choosing the right solutions, right projects, whereby we can make good headway in terms of innovations which are India-centric. So let us go back to Dr. Bansal, Nidhi.
So what a wonderful time to join us, Dr. Bansal, as we look at India at 75. I think the largest concern is to invest in healthcare. We'd love you to take your presentation and speak to all our viewers who've been eagerly waiting to hear you.
All right. First of all, I'd like to thank you, Professor Sharma, as well as Professor Verma, for giving me the opportunity to talk to you all. I'm going to try to do my very best, and hopefully you'll find it useful. First, I'd like to share my screen here. Let's see if we do that. Can you all see my screen?
Yes, sir.
Okay, so let me start here.
Yes, we can see it now, sir.
So I'm going to talk about four things. First thing I would do is talk about what is PSA technology. Then I'll talk about how to design PSA plants, and then how to use them. And I also would talk a little bit about what are the areas for improvement that exist, if someone wants to work in that field. So before I start on PSA, I like to talk a little bit in general about how the oxygen is produced and sold at the present time. So most of the oxygen in the world right now is produced using cryogenic air separation plants. Their air is liquefied and then it is fractionally distilled in a distillation column, and it makes oxygen, nitrogen, and argon, which is then provided to the user. If the user is a big user, these plants are on site and they are provided gases through a pipeline. But for smaller users, it is then transported by trucks. Typically, first of all, these plants are extremely efficient. They recover 100% of the gases in the air, in the sense they produce 100% oxygen, 100% nitrogen, and 100% argon. Typically, these plants are pretty large. They are quite complicated, requires a lot of operating staff. Typical plant sizes range in 400 tons per day to 2,500 tons per day. Just to put this all in perspective, a typical hospital would only use 2 tons per day of oxygen. So there is really no way that these plants would be put on site at the hospital. These are just too complicated and too big. To transport oxygen, gas is very low density, it's very high volume, you need to compact it. And the most compact form of oxygen is liquid oxygen. It is like 900 times more compact than gas. So oxygen is liquefied and then it is supplied by trucks. This is the easiest form of delivery. Only a driver is needed. He can drive the truck to where the oxygen need is, and he can connect it with a pipe and turn the pump on, and the oxygen goes from the truck to the storage tank. The only problem with this type of transportation is you need very specialized trucks. These are very high, super insulated trucks, because the oxygen you're carrying is minus 300 degrees Fahrenheit. And the storage tank also is super insulated. So, and that super insulation basically is very high vacuum. These are not pressure vessels. So one of the problem is that irrespective of how good the insulation is, there is some heat loss and oxygen always boiling, and it is building up the pressure in the storage tank. And it's not a pressure vessel. When the pressure increases to a certain point, it vents. So there is a small amount of oxygen which is all the time being lost. When you have a brand new tank, it loses about 2 or 3% of oxygen every day. But as the vessel gets old, and if there is an issue with the vacuum, you could lose it much, much higher. So the thing is, either you use the oxygen or you will end up losing it. It's not going to stay there for a long time. The other way to transport oxygen is through high pressure cylinders. Here you raise the pressure to about 2,500 pounds. So you are compacting the oxygen about 175 times. And the pressure is very high. So these cylinders are extremely heavy. A cylinder probably would weigh close to 200 pounds and would carry only about 20% of the weight in oxygen. So a 200-pound cylinder carries about 20 pounds of oxygen. And the problem with these is the delivery is very difficult. You have to load, unload the cylinders. You have to connect them and disconnect them. It's a high pressure cylinder. That's a safety issue. And also when the cylinder reaches a lower pressure of maybe 100, 150 pounds, it's considered to be empty. So you're losing 10, 20% oxygen just with those things. But the good thing about it, that there is no leakage of oxygen. You keep it. If you are not using it, it's not going to get lost. It's always going to be there. So in certain cases, this is a better option. And then like what happened in India, there was not availability of oxygen. So even though transportation could be done, but there was no oxygen. So if there was a way to put an on-site plant at the hospital itself, that would be a better solution. And that's where the PSA comes in. And major thing about PSA type of is has no limitations on the size. You can make it extremely small, like you can see the picture of this oxygen concentrator, which is, very small. You see the glasses like next to it, or you can make it pretty large. You can make it up to 125 tons per day. So it basically fills the gap between cryogenic plants and a small user. How it is, so I'm going to talk a little bit about how PSA works. PSA uses adsorbents. PSA is like pressure swing adsorption. And the reason we call it pressure swing adsorption, because during the process, we swing the pressure in two levels, high pressure for adsorption and low pressure for desorption. There are other ways to regenerate the adsorbent, like temperature swing adsorption, that would be called PSA, and that's used for certain application. And there is also displacement. So I'm not going to talk about any of those things. I'm going to stick with pressure swing adsorption, which is the topic for today. So basically what we are doing is we're using these beads, which is the adsorbent called molecular sieve. And it has special property. It can adsorb a lot more nitrogen at high pressure and then much less at low pressure. So we pass air through this adsorbent, and once it absorbs all the nitrogen, oxygen comes out as product gas, and when it is saturated, when we depressurize it to regenerate it. The adsorbents which we are using for this particular application, they're called zeolites. They occur in nature, but those are not really that good. So the zeolites which we use, they are synthetic zeolites. They're made in the factories. These are complex elements of compounds such as aluminum, silicon, and sodium. Main thing is these are ceramic materials and they are non-flammable. They're extremely porous. When I say extremely porous, they have very high surface area. A gram of that would have close to 800 square meters of surface area. So that's what the major property of these is. These are extremely highly porous. And then that powder adsorbent is mixed with some binder and turned into beads. Main thing about these things is that the gases or whatever it absorbs mechanically. There is no chemical reaction. That is the main reason why this thing works, because there is no chemical reaction and it's easy to dissolve. Whatever it absorbs can be easily dissolved. How do these things work? Molecular sieves, they are like little magnets. They attract polar molecules. As you know, all the molecules, they are all electrically neutral, but on a localized base, on a very localized level, they have positive and negative. Like for water, you have 2 hydrogen and 1 oxygen, and 2 hydrogen atoms are bonded on one side. So even though it is electrically neutral, but on a localized level, it's very highly polar. So molecular sieve attracts those polar molecules. Oxygen and argon happen to be not very polar. So these are not much as absorbed by this. The other property which the molecular sieve has, they screen out molecules. You have highly porous structure, and those pores are of a certain size. You can control those pores. And in hydrocarbon separation, if you have very large size molecules, they don't go into the pores and they can be separated that way. However, for air separation, we don't use that particular property because oxygen molecules and nitrogen molecules happen to be very close in size. So there is no way to separate them based on that. We are separating them based on the first property, which is attraction to the polar molecules. So if we look at the relative strengths of adsorption on molecular sieve, water is the most strongly adsorbed component, then is carbon dioxide, then any hydrocarbons, and then it adsorbs nitrogen. As I said, oxygen is very weakly adsorbed, so it's sort of almost all of it or most of it passes through. And argon, which is completely, all of it passes through. So the way a system would work is that we would use a vessel, which we call adsorbent bed, fill it with a sieve, and we pass compressed air through it. And as the air is going through it, all of the nitrogen is being absorbed. What comes out is oxygen and argon. And this is, there is 1% argon in the air, but by the time it gets through, is comparatively 5% to oxygen, 1 to 5. Oxygen is getting concentrated 5 times, so does the argon. And that is a big limitation, that the oxygen produced by a PSA is maximum 95.4% pure. Now, this can be purified by using a secondary purification system, but that's never a practical thing. It's not economical. It is quite expensive to do that. So the main limitation for PSA oxygen is that 95% purity is the maximum you can achieve. And there are certain applications where you need more purity than that, but medical is certainly not that. In medical use, you can use anything above 90% is good enough. So just to talk a little bit about how we design these things, these are the 2 isotherms I showed. These are relative isotherms for the molecular sieve which we use. As you can see, there is a lot, the top curve is for the nitrogen adsorption and the bottom one is for oxygen adsorption. Even though oxygen goes through it, but part of it does get adsorbed on the sieve. So our recovery in a PSA plant is never 100% like in cryogenic plants. So what we have to do is we have to pick 2 pressure levels, one pressure level for adsorption and the other pressure level for desorption. Typically, for a practical system, the ratio of the adsorption pressure to desorption pressure is about 3. So in this example, I'm showing a PSA using desorption pressure being the atmosphere pressure. So I'm compressing it to 3 bars, and this much amount of nitrogen is absorbed. When I depressurize it, only this much remains. So this differential loading will be removed every cycle. Now you have a choice of picking these 2 pressures anywhere on this curve. And if you look at this curve is quite steep as you go to lower and lower pressures. So there are certain applications where you may want to pick a pressure which is on the lower side. So in this case, I picked a pressure which is less than the atmospheric pressure, and that would be vacuum. And if you look at the differential loading in this case is higher than the differential loading in the PSA system. So naturally, this system would be slightly more efficient if you pick the pressure lower and lower. But the problem with that is, not the problem, but the thing with that is that you would need extra equipment. It would make the plant quite complicated because now you have to have a vacuum pump as well. And also, it is the adsorption pressure which provides the oxygen. So the oxygen pressure for delivery is at the adsorption pressure. So in a PSA, your adsorption pressure is high and you will not need, most probably, an oxygen compressor. On the other hand, if you go to these lower level pressures, then you would also need a oxygen compressor, which are very special items, require a lot of maintenance, and also there are safety issues. But when you are making very, very large plants, it is more practical to have VPSA because they save a lot of power. And they have operators who can operate these things. But for smaller application like hospitals and all that, PSA is definitely better. It's much simpler, much easier to operate, and much more reliable because there are less moving components. So the basic PSA process would have 2 steps. One would be the adsorption step, where the nitrogen is adsorbed at elevated pressure and oxygen is generated. And then there is a regeneration step where nitrogen is desorbed and the adsorbent is regenerated. So to show you how this thing works, here is a pressure vessel. Here is a pressure vessel, consists of adsorbent. You take a compressor, put a valve here, and the air is going into the system. And then you have another valve, much smaller. so that you can maintain pressure here. Oxygen is coming out and is going into this receiver, which is then supplied to the user. So that's all for the adsorption step. For desorption step, you have to add another valve, which we call waste valve. You close the, you close the product valve, you close the feed air valve, and you open a waste valve. All the nitrogen from this will come out through this valve and be wasted. And during this time, the oxygen would be supplied to the user from this receiver tank. So as you see, it is a step process and it's not continuous. To make it continuous, what you do is you add another bed to it. So now the system would look like this. So the way it would work is that you open this valve, air is going into this, and oxygen is coming out from here to the receiver tank and supplied to the user. While that is happening, you open this waste valve and the nitrogen is being desorbed and going into the waste. So you flip it back and forth. So that's how the basic PSA process works. And if you have a VPSA, then you add a vacuum pump here on the waste line, and you still do the same thing. You basically, there is no difference between VPSA and PSA. It's just the pressure level which are selected differently. So both of these things work like that. Now, a little bit about design. So if we look at a pressure vessel which had a sorbent and we pass, can you see my pointer? Can everybody see my pointer?
Yes.
Okay, so air is passed through the bed and nitrogen is getting absorbed, and then part of it is fully saturated, and then the oxygen level there is 21%, but as it goes through the bed, the oxygen level is increasing because we are trying to produce 95% pure oxygen. At a certain point, it becomes 95. And that is the only active part of the bed. From the time where it starts separation up to when it becomes 95%. So this part of it is called mass transfer zone. And we can only put air through the vessel until this mass transfer zone moves up to the top of the bed, and then we start having breakthrough. When we have a breakthrough, that means lower purity oxygen would start come out. Okay, so the major design thing is that we must have a vessel which can contain this mass transfer zone. And the second thing we have to do is we have to maintain the stability of the bed. Now, the basic process which I showed you, just pressurizing and depressurization, that really does not work, because what happens is that your mass transfer zone is so long that you cannot contain in a bed. So you make some oxygen, but it is very impractical to just pressurize and depressurize the system and be able to make some oxygen. So in design, what we have to do is we have to modify that basic two-step process and to try to make that mass transfer zone sharp. That will give us more ability to produce high purity oxygen. And the other major thing is there are a lot of things going in the bed when you're pressurizing, depressurization. We have to make sure that we do everything at a rate that we can prevent any fluidization of the particles, because if there is even the slightest fluidization, that will ultimately end up powdering the adsorbent and it will all go into your oxygen receiver and the plant would stop working. So there are two steps, as I said. One is going pressurization, we are going upwards, we have to prevent fluidization. The second step, when we depressurize, then there is a lot of dynamic force which is on the sieve at the bottom and it can crush the sieve. We have to make sure that doesn't happen. So I'm going to talk about what are the process improvement steps which we add to that basic PSA process to make it practical. So there are three steps we add. One is called the equalization step, and I'll explain all of these in much more detail later. It basically, the sieve, beads which we are using, they are round beads. And anytime you fill a vessel with anything round, you have minimum 30–40% of void space. So there is always air in that void space. Every time we depressurize, that gets lost. And that is a lot of loss of efficiency. So we use an equalization step which takes care of that problem. We also add what is called a purge step, where we use some oxygen which we are producing to purge the last remaining nitrogen. It also helps sharpening the mass transfer zone. We do the same thing. There is a step I will explain later. It's called oxygen repressurization step. That also is to sharpen the mass transfer zone. The major thing about design of a PSA plant, especially a 2-bed or any kind of system, is that the beds must be completely regenerative. Every cycle, it must be completely regenerate itself, both in terms of mass as well as in terms of thermal. I haven't talked about thermal things at all, but to just give you a little bit information, adsorption is an extremely high exothermic process. So when you are adsorbing, there is a lot of heat coming out. And when you are desorbing, all of that heat must be given back to the bed. And it must be exact. You know, it's not a very major problem on small systems, but in very large systems where you have some heat getting taken out by the product oxygen, you can have thermal deficiency and you can end up freezing the bed. I have had very, very bad experiences in the field early on when we were making these plants. They would freeze and then we'll have to wait for days for them to unfreeze and start working again. And there is, I'll explain a little bit, how do we optimize all these steps? You know, we take samples at the product end. Product end is where oxygen is being produced, and the waste end is where the waste is coming out. With the oxygen analyzer, we can take waste and product profiles and use them to optimize this process. So coming back to what does equalization means? Equalization, as I said, we have round beads and there are void spaces. We are trying to save that air. And the way we do that is to the basic process, we add another valve. We close every other valves, and this bed is at high pressure and we want to depressurize it. Before depressurizing it, we open this valve. Part of this air would go into this bed and this pressure would drop, and then we will open this waste valve. So that way we saved half of the air. Now, if you had 3 beds, you could save more, but the more number of beds you put in, the more number of valves, and it becomes more and more complicated. The design, you know, PSA designs are done specifically for the application. Every application would need a different kind of design. And I'm not going to try to complicate it any more than this. Purge step, the way we do purge is, again, we add another valve on the product side, which we call purge valve. So in this picture, you see air is being fed into this bed and oxygen is coming out, and this bed is producing oxygen. So we take part of the oxygen which is coming out and we put it in this bed, and that's what is called the purge step. Actually, this valve should be open. This valve is shown red, but it is open and the nitrogen is being pushed out through this valve out into the waste. That's the, I'm sorry, purge step is this. So in purge step, the air is going into this vessel and oxygen is produced. Part of this oxygen is going into this purge valve, coming and pushing nitrogen out through this valve. This is the purge step. And the third step, which I talked about, is repressurization step. And that is what we do is, it's the same step as before, except that we close this waste valve. So the oxygen which is coming into this bed raises the pressure of this particular bed little bit. And that's what is oxygen repressurization. So I'm going to show you how these things ultimately work later on. But before doing that, another very important aspect of design is to protect the adsorbent, because adsorbent is the heart of the system. It's the most expensive part of the system, and that is what makes the whole thing work. And as I said before, there are 2 issues. when you are feeding the air, you have to make sure that the beads don't fluidize. It is a packed bed, and that's how it has to stay. If your feed rate increases for some reason, or the velocity is increasing, or if the bed is not properly designed, you would end up getting small fluidization, because there is a range of particles you have. Nobody makes perfect size adsorbents. They all, like the adsorbent which we used is 8 to 12 beads. They go through 8 screen size, but they are retained on 12 screen size. So some of the particles are small, some are large. You have to make sure that every one of those particles stays where it is. It cannot be moving. So that is the fluidization protection. And then when we are depressurizing it, there is a lot of dynamic force which is acting on these particles at the bottom. And we need to make sure that we don't depressurize very fast, that these sieve gets powdered. So we have to protect, and I'll show you how we protect this. As I said, fluidization prevention is the most important thing. That determines everything about the design of the plant. That determines everything about how big the diameter of the vessel has to be, because you know how much air you want to flow through it, and the diameter of the vessel will determine what the velocities would be. You know what particle size you're using. You can calculate what the fluidization velocities are, and then you have to maintain the velocities less than that, and that determines the diameter of the vessel. And then the length of the mass transfer zone will determine the length of the vessel. So to protect fluidization when it is in upward direction, it is a question of selecting good diameter for the vessel. And the second thing, when we are depressurizing it, there are 2 times when you have potential fluidization. One is when you are pressurizing the vessel, and second thing is when you equalize, you open a large valve, because you have very small time to equalize the bed. And in that, when you're equalizing it, there are flows upward in this vessel, but there are flows downward in the other vessel. And if you have an equalization rate which is faster or which is very high, it will end up crushing the sieve here. So you need to make sure that you don't crush this. So what we do is we add some flow restricting devices. And that's called flow restricting devices here. You size the valve like that. So that's how you prevent the fluidization. For everything which I'm talking about, that is applicable to hospital plants. Also, it is applicable to small concentrators for home use. When we design concentrators for home use, the design criteria is that it must be very, very small, because it has to be portable. So some of the things, how we miniaturize it is by using very small size adsorbent particles, because that will provide you more surface area. They're more efficient. But when you use very small particle size, then there is no way to protect fluidization, because the velocity, the particle size is so small that even the smallest velocities would fluidize those particles. So for those, what we have to do is we have to design the bed differently. The vessel we constrain it from the top. So we put a moving piston on the top, and so it doesn't let it go upward and fluidize. Now the question is, why do we put a moving piston? Why don't we just fill it all the way up to the top? And then there is no moving piston and machine parts required. But the problem is that no matter how you try to pack the adsorbent at the start, you put it on a shaker table for an hour or 2 hours or 10 hours, there is no way to pack it as good as it will get packed by itself when you start to pressurize and depressurize. So when you start to pressurize and depressurize, every time it moves up, moves down, it's like somebody is banging on it all the time. And there is always some settling in the field. So unless and until you have a moving piston, the sieve will powder. It is extremely, so the bed design can be different for concentrators. And the thing about now, one thing which I mentioned, to prevent crushing of the sieve, we cannot be depressurizing it very, very fast. But in PSA process, we do need to depressurize it fast. We don't have too much longer cycle times. You need a lot of adsorbent. So what we do is, for the waste valves where we depressurize, we put 2 valves and we open them sequentially. We open a small valve first and let the bed pressure come down to a certain level, and then we open the second valve to depressurize the rest. So that is the way we do the depressurization. In large plants, you need all these things. In smaller plants, like in concentrators, you can combine functions of these valves, and I'll show you how you combine them. So everything I've said is applicable to large plants as well as concentrators. So in terms of nomenclature, everything on the product side is called product manifold. Everything on the air side is called feed and waste, because that's where we are feeding the air and also we are letting the waste out. I need some water. So I'm going to construct a little PSA cycle. It's a very typical PSA cycle, and it is applicable to large plants, small plants, as well as concentrators. The PSA cycle doesn't change. So here is a PSA plant, which I showed. The first step, we have to start someplace. This is A bed, this is B bed. We're starting B at the lowest pressure and A at the highest pressure. The first thing we do, first step, we open this equalization valve and we depressurize this A bed, and we take the air, put it into the second bed, and it is pressurizing. And the only valve open is this equalization valve. So this is how the pressure profile would look. And in this particular case, I can't see my screen. Just move this more. Okay, so this step is 10 seconds. And these are different, every design would change, but I'm just using, typically that's what we've been using. So the first step is equalization step. Second step, we add it after, we're still feeding bed B, going pressure up, and we now B pressure is, and now we open one valve on the waste side on A. So the A is still depressurizing. And this step, this is the flow directions I showed here. This is the pressure levels. And these are the valves which are open. So this is 5-second step. And now we are at these pressures. And then the next step we add is we now open the second feed waste valve. It's still the continuation of the number 2 step, but it is just bringing the pressure down, pressure up. And these are the valves which are open. This is about 6 seconds. And now comes the main step, which is the production and the purge. Production, this is the step where we are starting to now take oxygen. If you look at this now, this is air side, this is oxygen side. This arrow shows that now we are producing oxygen from bed B. And at the same time, we are taking part of the oxygen and we are purging it. You see the purge valve is open, so bed B is purging bed A. And this is the longest step. This is the oxygen production step. In this case, it happens to be 20 seconds. And then the next step is, as I mentioned before, we repressurize with oxygen, slight repressurization that makes the process much more efficient. In this particular case, now this bed A is getting repressurized from the oxygen from this bed. So that is a typical PSA cycle. And then we just reverse it. And this is the 2 bed and keep going back and forth. So this is how we construct the PSA cycle. I have to see what time. So when we look at the overall plant, we will have components. We'll have an air compressor with all its moisture separator, after coolers and all that. And we have a PSA module. And if there is a oxygen compression or storage required, there would be oxygen compressor. And then we have a plant control system, and then oxygen is being supplied here. what's the function of control system? The PSA control system, it operates the process valves and maintain the normal cycle sequence. We can also override it during startups. For larger plants, smaller plants don't need all that. And the main thing is that if there is a failure, if there is a power shutdown and all that, it has to shut down in a fail-safe manner, because if the certain valves are left open, they will suck in air from the atmosphere and it will end up contaminating the cell. So that's the purpose of the PSA control system. I'll tell you how we do it. We take signals from all the valves. We take signals from all the sensors we put in the plant. And these can be, depending on what the application is, what the user wants and all that. We take all these signals to a PLC controller, and then we can program it any way user would want it to be. That depends on user, what he thinks are important things for him. And that's how the PSA plant is controlled. Typical layout would be, we just, if the plant is not very large size, specifically for like hospitals, that's how the installation would look like. The PSA plant is not really that big, 2 tons per day. A typical hospital doesn't use that. So this is how a typical installation in a hospital would look like. We'll have a mechanical room. We put all these things in there and it's good to go. Now for a large plant, a very, very large plant, we built, these cost millions of dollars there. These are the adsorbents. I'm just showing you these pictures. These are the adsorbents. This is the air receiver. And, these are cars. We put cooling towers. And this building would then have all the compressors and all the control panels and things like that. So PSA plants go from portable concentrators to field installation like this. On a concentrator, now for the kind somebody would use at home, we eliminated the second valve because these beds are very small. We can depressurize them reasonably with one bed with one valve in a reasonable time. Also, we are able to eliminate, we are able to combine the purge and the equalization and the oxygen repressurization function in one valve. The cycle will still stay the same, but we can use one valve. And also we can eliminate those product valves just by replacing them with check valves. And the process, but the rest of the components are the same. You still have a compressor. These are a noise attenuation thing. You still have all those components, but you simplify them because the idea there is to make them into a very small package. A typical package would look like this. So what you have here is a compressor. This is the aftercooler cooling device. This is the oxygen receiver, and the 2 vessels which I showed you with the moving pistons, those are on this side. So all of those things can be put into this small package. And this is the noise reduction part, but they all, as I said before, the cycle sequence and the cycle is still the same. It's just the miniaturization of components. So there is no difference between a large plant, medium-sized plant, or a small plant. They're exactly the same thing. The consideration and the design and all that is exactly the same. Only thing is, in a concentrator, you're trying to reduce the weight. And also, as it is going to sit next to the patient, it has to be very quiet. And to try to quiet that is a very, very big issue. You put lots of foam and all that. And the problem with that is when you do that, you retain a lot of heat of the compression within the cabinet, and that is very harmful to think. So there is an optimization which you do between the practicality of the process and also the quietness of the system and the size of the system, but they are the same. Okay, so now how do we use it? How do we use it? We have an on-site plant now. It's a mechanical system. And it has its issues in the sense it can break down, the power can fail, all sorts of things can happen, but you are supporting life. So you are not going to use it by itself. It's just never advisable to use a PSA plant, not PSA or any on-site plant, mechanical system to support a life. You need to have backup. So PSA alone itself is not going to be the solution. What you have to have is you have to do a little very back of the envelope type risk analysis of a hospital site, and then you provide backup to it to that system. And the backup could be liquid oxygen, and it could be high pressure cylinders. And I'll tell you how these things are combined and what are the limitations there as well. For home concentrators as well, when the patient is using this oxygen concentrator at home, he can use it, but these are 40 pounds or 30 pounds. He's not going to carry them when he's going shopping or something. So, and also even at home, you can have power breakdown and all that. So he needs to have a backup supply. These are small oxygen cylinders given to him, or it could be a liquid tank given to him, which he can fill his small walkers and all that. So how to use them? Most standards recommend that there should be 3 sources of supply. Specifically, when you're using them in hospitals for supporting life, you have to be absolutely sure that the oxygen is available all the time. So they recommend, and these can be combined in certain ways, that there should be a primary supply of oxygen. It's not only oxygen, all the medical gases which are connected to hospital pipeline, they should have 3 sources of supply. Here in this case, there should be a primary supply, which can be a PSA plant. There should be a secondary supply, and I'll tell you how to size these things. It can be high pressure cylinders or a liquid tank. And then there should be a reserve in very, very big emergency. And a reserve supply can never be liquid, because as I said, you're not going to use it. It's just going to sit there until you have a major emergency. And liquid storage is not good for that, because it just does not hold oxygen. If you don't use it for some time, you'll end up losing it and there would be nothing available. So that is the major difference. So primary supply, and there was a lot of questions asked to me, how should a hospital size the plant? In my opinion, or what is the standard, is that the PSA plant should provide the average consumption of the plant of the hospital. Now, hospitals do surgeries in the morning, they do different things in the afternoon. So there is not a constant demand. It changes. There is sometimes peak demand. And to size a plant, PSA plant for peak demand will give you a plant size which is way larger than what they need. It would be more complicated, more difficult to maintain and all that, and there is no need. It will just sit there. So it is recommended that it should be sized based on average consumption or your projected average consumption in future. And then, you can also use similar experience from different hospitals. Now there are lots of hospitals in the world who are using these things. So there is a lot of experience there. There are lots of papers available. People can read and all that. The secondary supply. The secondary supply, as I said, could be a liquid oxygen tank or could be high pressure. And that is to supplement the oxygen during your peak load. Whenever there is a peak load, it comes from there. And also, if you have loss of power and all that. Now, reserve supply, as I said, it has to be high pressure cylinders. And the way you have to size it, you have to see where the hospital is located. How far is it from where you can get high pressure cylinders? How long would it take to get the high pressure cylinder replaced? Because once you start using reserve, you better be ordering more cylinders from that plant. And if it takes 2 days to get this delivery, you need to have at least those 2 days. And how many times a week you can get it delivery? If you can only get delivery once a week, you need to have another 7 days worth of oxygen. So there are ways, this is again, I'm not suggesting that somebody should down and study a risk analysis for a year or something. I'm just saying a risk analysis worth maybe an hour or half an hour, just talking about the users and all that can be sufficient. But these are the considerations which people have to keep in mind. Okay, now I'm just going to talk a little bit about what are the areas where the improvements can be made. I'm not sure what the audience is, but for those people who are into research and want to work on these things, they could look into main thing with these plants. It's the adsorbent itself. And, that is the heart of the system. That is, if you can improve the adsorbent, in terms of porosity or selectivity or its absorption capacity, that would be of great benefit in the sense it will simplify the plants. It can make them smaller. So this is really, as I said, is the main thing. And also these adsorbent itself is in powder form. It has to be made into beads. So there are binders which are put in, and the binders determines how strong the bead would be. That is, if the bead is strong, you don't worry about crushing strength and all that. You can again simplify the system. Also, binder is a useless thing in the sense it doesn't absorb anything. So if you have too much binder used making those beads, that's not good. So people have tried to make beads which are called, binderless, sintered. They sinter those things. But when you do those sintering and all that, then you lose porosity. So there are opposing things which happen. But there is a potential to improve binders and adsorbent ratio, bead sizes, again, could be different. Smaller beads are more, they give you more surface area for absorption, but on the other hand, they are difficult to contain and all that. So these are some areas. I'll just show you how these things are made. Typically, you take all the components, you put them in, you synthesize them, and then you do some ion exchange. You add different ions, then you add binder to it, then you mix them, then you turn them into beads or pellets. And in the end, everything then needs to be activated. And this basically, you raise the temperatures to 1000 degrees or something for a certain amount of time to drive off all the water. And then it is the adsorbent which you use. In older days, 10-15 years ago, most of the ion exchange was calcium. We used to use these 13X 8x12 beads, and they did the job. We still use them in certain things. They're relatively inexpensive. But recently, instead of calcium, they started using lithium. And that actually changed everything. It made the adsorption capacity very high. It also made the selectivity very high. And these adsorbents, now, but they're expensive, but they are extremely efficient. The sizes of the plants have gone down quite a bit. I'm not sure lithium is the ultimate thing, but right now that is the best. Maybe somebody can look at these things and maybe come up with something even better. So these are, areas where, people can do some research and think about these things. On the PSA itself, I gave you cycle steps, which are typically used these days or today, but, nobody's done, these are based on my own experience of last 30 some years. We think it is quite efficient, but again, there is always potential to improve the process efficiency, cycle steps, pressures, what the pressure levels are, how the flow rates are, because flow rates are extremely important. Whenever you're passing air around a bead, you have two different resistances. You have film resistance outside, and then you have the resistance of inside the bead itself. And the velocity will determine which one is the controlling one. So there are things which can be looked into these things. Also, I showed you a lot of components. There are lots of valves which are needed, PLCs, telemonitoring, all these things can be looked at and improved upon. It's not the ultimate what we have. And the next thing, it's always difficult to do laboratory experiments. If you can simulate something on the mathematical modeling side, it's always cheaper to do. At least it gives you a starting point to start making the setup for experimental. Now, I put it out there. It is quite involved because there are, I did not talk too much about what is involved. It is, as I said, it's a mass transfer and also a lot of heat transfer. You have multi-component adsorption. So there are a lot involved. They haven't been able to make a very good modeling for this. Again, somebody can think about it. It's been done for the last 30, 40, 50 years. We never really used it, but there is potential areas here. Now, as I said, everything I talked about is applicable to concentrators as well. Concentrators happen to be a little different in the sense, noise is a very big deal. Noise attenuation is a very big factor in concentrator design. And, there are opposing things. If you close it down so the noise doesn't come out, it becomes hot. So there are noise attenuation materials. People are talking, this is a reciprocating compressors. They sit on these vibration mounts. If you make the vibration mount very light, then, it is quieter, but then you cannot ship the concentrators because They all break. The compressor weighs 5-10 pounds. People are talking about using noise cancellation technologies. Somebody can look at that. Maybe that will change something. And ultimately, we are always looking to reduce the size and weight of concentrators. So there is potential things which are somebody can look at. So I think maybe I talked too much, and this is basically all I wanted to think. Yeah, this is all I wanted to talk about, and I'll open for questions.
Thank you so much, Dr. Bansal. That was indeed a very enthralling presentation on highest possible efficiency and the PSA oxygen solutions for hospitals, the one-stop solution actually. और यूं तो भारत में कहने को 10 से 12 मेडिकल ऑक्सीजन के बड़े निर्माता हैं और 500 से अधिक छोटे प्लांट हैं, मगर उन सब की एफिशिएंसी बेहतर करने का तरीका आपने साझा किया आज. इसके लिए बहुत बहुत शुक्रिया. और and this is very vital for all of us to learn from this information. And as we speak, there are a host of questions which are just pouring in. But before that, I now request Professor Sandeep Verma ji, Secretary Science and Engineering Board of SERB, to please say a few words on today's excellent seminar. Sir.
Thank you very much, Dr. Bansal, for taking us through the nuts and bolts of oxygen concentration, the PSA technology. And I think it is now clear to most of us that this technology and the whole concept of these larger plants as well as home sort of devices that can be installed at home requires quite a number of innovation. It has quite a number of moving parts. A lot of optimization is required to get the optimal output of oxygen at the end of the day. And when we correct me if I'm wrong, when we look at the innovations or the kind of moving parts that are going to be really important and critical for delivering the best possible output, there still exists quite a bit of window where we can make differences, where we can make innovations which are India-centric, and perhaps be on the way where we could achieve some kind of self-reliance in manufacturing these concentrators for current use, for use in near future, and for posterity, for patients who are sitting at home and they require pure oxygen for their ailment or for just the well-being. So I think there are a lot of questions. I really thank you on behalf of SERB, on behalf of Professor Ashutosh Sharma, Secretary DST, for providing us this insight. And we hope that there would be a lot of questions. A lot of people would like to connect to you at some point of time for seeking advice to how to move forward if they have stuck at some place. So we look forward to these exciting deliberations, the question answer session. And at this moment, I can only thank you and cannot thank you enough for your time. Thank you, Ravi. Very, very much appreciated. Thank you.
Well, thank you, Dr. Verma. One comment I like to make, as I said, these plants, they require a lot of moving components and all that. So there is always a service issues with these things. Hospitals are not, they are not plant operators. They save lives. They do surgeries. So it's very important to have a service organization who is watching these things, from time to time and all that. So the most important thing, there are a lot of people who are selling these things, in the world and, even in India as well. And I would just suggest that people look at a provider who has the biggest service organization. From what I know from here, the distributor for AirSep is Aerox. I think they have put in like 700 some plants, and they seem to have the largest service organization, at least at the present time in India. And I'm sure others will catch up or something, but until that happens, I think, AirSep probably is a good choice. That's my little plug for my old company. Okay.
Thank you, sir, once again. And may I have your permission to begin the question answer session, Dr. Bansal?
Absolutely, please.
Yes, sir. So the first question is, how much impact would the change in zeolite make to the technology if the oxygen level is around 98 to 99%?
Okay, first of all, it's
Dr.
not going
Sujit
to happen.
Sen has also asked this question, sir. There are 2-3 people asking the same question, so perhaps you could deliberate on this.
First of all, the way the molecular sieves work, they just don't absorb argon It's the most weakly absorbed component, so it all comes out in the product. So from a one-step PSA using a zeolite, it's never going to be happening that you will make more than 95% pure oxygen. However, there are ways using PSA to then further purifying this. And the process which I talked about, it is based on stable equilibrium. Every time I pass air through the bed, it comes to an equilibrium and it absorbs more nitrogen than oxygen. However, we can make a rate-based process, completely different design, using different adsorbent, and the adsorbent in that case would be carbon-based. It's called carbon molecular sieve. And you can put a secondary PSA plant using carbon-based adsorbent and then use a rate-based process. I have done that. I have patent on that as well. But again, it is, you lose to try to remove last 3% of impurity, which is argon, you lose 50% of your oxygen. So your recovery is only 50%. In extremely, special applications, that is still a good thing. But otherwise, it's just not very practical thing. Cost is always an issue for medical. For 20, 30 years, everybody claimed that you need 98, 99% pure oxygen because those are the standards. Those standards were written by gas companies. And there was no other way to produce. They were producing 99.9% pure oxygen. So nobody let us sell these plants into hospitals. I sold these plants into hospitals only in the extremely remote areas of the world. Island countries, I traveled 30, 40 countries every single year for 30 years. And never to a city, always in the jungles or wherever, But now suddenly with COVID and all that, all those standards went out the window. Nobody is dead. There are so many papers which have been written showing how good this oxygen is and how it can be used. Even 20, 30 years ago, military hospital, the field hospital were always using on-site plants like this because they did not have access to cylinders or liquid oxygen. So these were being used in hospital in specialized cases. But now with this COVID, the purity issue for hospitals and most of the application is not there. Only time high purity is required, the only single application I know of is cutting of the metals, where you need to have 98, 99% pure oxygen. If you have argon in there, it creates a lot more slag. So there are very few applications. Anyway, coming to the question, yes, it can be done, but it's not going to be done in one stage. It will require second stage. At least that's the present day technology. I hope I answered the question.
Absolutely, sir. And now I'm going to club two questions because a part of that you've answered already. Why is this PSA technology so undersold in health sectors worldwide? And the next question is, please explain how repressurization steps help in increasing the overall efficiency, if at all. And is it possible to use different sized absorption also for preventing fluidization? Sir.
I think I answered the first question. Why has it been used in the hospitals? I told you because the standards were written by the gas companies. Only 5 to 7% or 10% of the oxygen in the world is used for hospital applications. But by calling it medical oxygen, they were able to charge 10 times the price. 30, 40% of the profits to the gas companies come from it. So they were, even though this PSA technology was developed by them, I did not invent it, but they never tried to put it out there because if you sell capital goods, a capital plant is only one-time sale. Consumables is always more and more. And the only difference between medical oxygen or industrial oxygen is the addition of a bacteria filter. You just add a bacteria filter down. Also the other difference they claim is that there's the quality assurance. Every time a cylinder is filled with medical gas, they evacuate the cylinder, they sample this thing and all that. But these are all made up things in my mind. And, I tried to be on the International Standards Organization panel, and I was one, and we spent 10 years writing the ISO standard for use of PSA in the hospitals. But all the representatives were from gas companies. in 10 years, we couldn't write the standard. I attended these meetings every place in the world. I ended up spending millions of dollars, but it has changed. A lot of countries have now changed to that. So that is why it was not used in hospitals, but it has changed completely. Now the standards would be written differently. Anytime a standard is written, it takes 10, 15 years. Every word is debated for long, long times. And then, depends who is the part of that committee. People like to get on it. I was fortunate to get on it for 10 years, but I don't know whether it was good thing or bad thing. I spent a lot of money. Okay, now oxygen repressurization step. It is just one of the steps which we found that it improves the efficiency. How it is improving, as I said, it sharpens the mass transfer zone slightly. Again, these were done experimentally, not theoretically. We tried different things and we found by doing that, we were able to improve the efficiency slightly. So that's all I can say about that.
Right, sir. Then the next question is, how do we take care of highly polluted air, which may be CO2, SO2 particles before it goes to the compressor or absorbent columns? And
No, go ahead. Sorry.
So, sir, you answer this. I'll take the next one separately.
No. I will answer it. All air, pollution, you have to have filters. We use filters before and after. We use carbon filters. We use moisture separators to take out all the water, condensed water and all that. And then also, as I said, the molecular sieve itself is able to absorb all those before it absorbs nitrogen. So what you will have to do is you would have to add additional adsorbent. Either you would add additional adsorbent so that the part of the bed is used to remove those things, or you could also sometimes at the bottom of the adsorbent beds, you use silica or some other adsorbent which is able to absorb those things. I've personally found that using just slightly more adsorbent would take care of all these things. And you have probably 1,000 or 1,500 plants which are running in India, and they're running there. Okay. Most important thing, the number one most important thing is that the plant be monitored every day. When I say monitored, somebody just need to walk by there and make sure that a drain valve is not stuck, or, there is a lot of dust in the air. There is a lot of, and a drain valve stuck is the smallest of the thing can end up ruining your adsorbent. And the way we protect these things, we put an oxygen sensor in there. If the purity starts dropping, somebody needs to respond and do something. You cannot just ignore. Problem is not going to go away. And that's why I was saying you need to have a good service organization behind it. But these things have been built, for 30, 40 years. They're quite reliable and they do work. And people who don't take care of them, they don't work and they come and complain. I lost millions and billions, again, I've put up with all these things for a long time.
Absolutely, sir. I'll go on to the next question now. How does one ensure that water being used for washing the oxygen to a patient is not infected? What happens in case of a power failure while using the concentrator? You said that in your presentation, but I want you to repeat it, sir.
No, again, as I said, it has to be, as I said, PSA alone would never be enough. You need to have backups for everything. That's why, I wanted to see how it is used at home or in hospital. And I did not get the question for that water. What was the question?
I'll repeat it, sir. How do you ensure that water being used for washing is not infected? I mean, the water with which you probably clean the machine is what is being.
I don't know where you use the water to clean the machine.
And again, sorry, the water to use. It's not been phrased properly. I'll go on to the next one then. Maybe you understood. This was happening in mucor cases. I think it's one of the significantly referring to that the oxygen concentrators need to be, used with proper water. I don't know what the viewer is asking.
No,
again, I think it has to do with mucor, in my understanding, sir.
No, the way it is, as I said, molecular sieve absorbs water the most strongly. So the oxygen which is produced has absolutely no water in it. The dew point of that is maybe 100 degrees or minus 100 degrees or something. So there is no water in that. And if the patient is breathing that dry oxygen, it can dry their mucus. But again, if it is being breathed in with a cannula, there is a lot of infiltration from the air around it, brings enough water. On the other hand, if you want to humidify it, there is always a humidifier bottle which is attached to the concentrators. There is a space for it, and that water has to be distilled water. There is nothing I'm going to tell from here, how to clean the water or
Absolutely.
anything.
So do the absorbents get deactivated on long-term storage? What are the precautions to be taken for long-term storage?
Okay, so that is one thing which I addressed. A PSA control system, that's its part to do that it has to be a fail-safe shutdown. Now, for example, if a concentrator is put in a storage, there is a temperature change all the time. In the night, the temperature is low. In the daytime, the temperature is high. When the temperature is high, the beds are going to desorb some part of it. And in the night, when the temperature goes down, it will try to suck atmospheric air from outside into the adsorbent bed. So now if there is not a check valve or something installed at the end, it has a potential of sucking in, over a period of time, it will become deactivated. But this is all the design of the system. These things, when we design these concentrators, and AirSep used to make 600 concentrators, 700 concentrators every day. And we dealt with all these problems. We made sure that we put in check valve, things which we did not even think about. Theoretically, when you try to design something, these things don't come into picture. They only come when the users abuse these things. And then, I wouldn't say abuse these things. That's a normal user. He's not. Most of the users of the concentrators are 80 years old people. Sometimes they used to even call us, the concentrator doesn't work. We send a service guy and they haven't even turned it on. So, and we can't blame them. This has to do with the design. Yes, the storage can cause problem, but a properly designed machine with check valves at the end would not let the air go back in. I hope I answered the.
Absolutely, sir. We have another question for you. Dr. Sujit Sen from NIT Rourkela is asking, any other effective type of zeolite other than X for air separation? Is there any other type of zeolite?
There are many, many different types of zeolites, which are, adsorbents, which are made for different type of separations. They have different pore size, they have a different structure. We use 13X, which is a X. I'm not a physical chemist, but I can just tell you 13X means 13 angstrom pore size, and X is the crystalline structure. Now I couldn't.
Absolutely.
So there are 5A, which has A type of structure, and 5 angstrom or whatever pores. These pores can be controlled. That is the difference between natural occurring zeolites and synthetic zeolites. Because in synthetic zeolites, you can control the quality and the homogeneity of, everything is exactly the same. And you can design a process around it. But if you use naturally occurring zeolite, you take it out of a mine or something, you don't know, you can never really design a plant around it. At least not replicate the same design again and again.
Absolutely, sir. The next question is, what is the effect of air temperature and humidity on efficiency of PSA, and how should we handle it, Dr. Bansal?
Well, humidity, again, we plan to have 100% humidity air go into the system. You handle it by designing your adsorbent bed and process in such a way that it can handle that. And temperature is always an issue. Temperature is always an issue in the sense, higher the temperature, the more humidity it carries. That's why we use refrigerant dryers after the compressor, but on a concentrator, you cannot use that. So it has to be accommodated in your bed in the amount of adsorbent you use. And, in India, I was recently reading a white paper which has come out, where they have done a study on concentrators, issues with in developing countries, and a lot of these things were addressed. I think it just came out within the past couple of weeks.
Yes, sir. Absolutely. If you could also mention some fluid restricting devices used in PSA/VPSA.
Okay, well, fluid flow restricting devices sounds like a big deal, but these are orifice plates. You size the orifice in a certain size. And again, when you have an orifice plate, first of all, any valve, you size the valve properly. But the problem with the valves is, you don't make it custom. You buy a valve, each valve has a different CV, and it may not meet what the CV you need for your process. So you adjust those CVs by adding restricting flow orifices, basically orifice plates. And also none of the valves are equally the flow, when the flow direction changes, they're not, the flow is not exact in the both directions. In one direction, it is a little bit more, in other direction, it could be a little bit less. And in PSA, the flow is changing both sides. So you take a bigger valve and you put an orifice plate, which is milled so well that it can have the uniform flow both directions. And also sometimes, to balance the beds, we used to make the orifice plate in a way we will round up the edges on one side and leave the edges sharp on the other side. That also can give you different flow in different directions. And that takes a lot of experience. When you make these things, both beds have to be exactly balanced. Balanced in the sense, when you get the adsorbent and you fill them, you're never gonna fill them exactly the same way, but those things can be accommodated by changing the orifice slightly. Again, that comes with experience. You don't design the plant every single time. You have the plant designed once in lab, and then you just fine tune it in the field. My technicians had gotten extremely good at changing the flows. These are small tricks of the trades which come with doing these things. It's not a theoretical thing. You can sit at home and make all these theories, and that's what we do. That's what the PhDs do.
And India has the best minds there. So using PSA technology, can we fabricate smaller versions of this as an oxygen concentrator? Is another question.
Well, we used to make a concentrator which weighed only 2 pounds. You can buy it. Why would you make it? It's less than 2 pounds total. And it produces, it gives you 3 liters per minute, but it doesn't give you 3 liters per minute. The concentrator only makes ½ liter per minute. But then in the cannula, you add technology where cannula can, monitor your breathing patterns. And your breathing patterns is when you're breathing in, your nasal cavity pressure goes down. That's why the air goes in. And when you're breathing out, your diaphragm in the stomach pushes that your pressure in the nasal cavity is higher so the air can come out. And if you put a pressure transducer in a cannula, that can monitor your breathing pattern. And typically you take 20 breaths a minute. So it's 3 seconds each minute, each breath. Out of 3 seconds, you breathe out for 2 seconds and breathe in for 1 second. So you put a valve and you close that valve for 2 seconds. So now, the concentrator will act like it is 3 times bigger. But also there is more, the only transferring mechanism in your body is your lungs and alveoli. You have trachea, which is doesn't do anything, but it has a lot of volume. So when you open the valve, you don't need to give oxygen all the urine inhalation. You give it the first half of the breath. You give a bolus of oxygen. So we used all those technologies to miniaturize these things. Now ladies can carry them in their purse. I mean, not exactly, it's a big purse.
Yes, got that. Another question, Dr. Bansal, is what are the changes required to the existing nitrogen PSA plant to convert it into a medical oxygen plant, if at all that's possible?
No, why would you want to do that? These are questions, we can question ourselves to death for everything. We need to see, a nitrogen plant uses carbon molecular sieve. It's a different, why would you want to do that? I like to know. Why would you want to do that? Or these are just hypothetical questions? No,
they're coming to me right now. And another one is steps for troubleshooting in case of any problem faced in your PSA. So I'd conclude with this.
What is that? What is the question?
Steps for troubleshooting. I'm just taking them from the chat box.
Oh, no. There are steps for troubleshooting. It is a pressure swing system. So you monitor the pressures and you stand there and see how the pressure are changing when the step is changing, the cycle is changing. And if it is not reached, we can troubleshoot these things. Basically, it will work if your pressure levels every time when the step, if I stand in front of a PSA system, my ears are tuned, I can tell what is happening just by the sound of it.
Right.
So it is not very difficult to do. It is not rocket scientistry. We're not sending rockets on the moon and all that. But I have to tell you a little story about that. There was a company called Ceramatech. The guy used to come to our company, try to sell me these oxygen sensors they were making, and we wouldn't buy them, and they went bankrupt. It was a technology which was using, making oxygen. And I don't know how much you're following. Now we have a Perseverance on Mars. And the first thing it did was make small amount of oxygen. And that is, for 10 minutes of breathing and all that. And the technology used was the one the guy used to come and try to sell me all the time. And I threw him out. But now it is the biggest thing in the world. But that thing cost over $100 million to make, and they made 2 grams of oxygen. So there is a use for everything. You never can tell what will be used where.
Absolutely. And on that very, very pragmatic note, I thank you, sir, for sharing your vision on introduction to PSA technology and its role in long-term oxygen solution for hospitals. We request you to join us on more occasions as the questions are still pouring in, but we need to close now due to paucity of time. I thank you, Professor Sandeep Verma. Thank you so much. And I thank SARB for having had this absolutely brilliant session. And in the end, I'd like to say to all our viewers that India's health sector can emerge as its biggest driver of growth and employment in pharmaceuticals, biopharma, hospitals, doctors, nurses, and medical equipment. It has a huge multiplier impact on the economy and on the lives of our citizens. And I thank you all with this, and I thank you all for watching. I thank the audience for watching. Thank you so much, Dr. Bansal, once again.
Thank you. Again, I have to thank Professor Verma and Professor Sharma to give me an opportunity. I'm a salesman. I talk all the time.
So we'll request you for another session. Thank you so much, sir.
Thank you.
And namaste to all our viewers. Thank you. Thank you for watching.
All right. Thank you very much.